lecture. Otherwise, I agree. I get like Friday is hard, you know, like I have crazy deadlines as well, and if I manage to survive until Friday, then I kind of check out often. Yeah, let's release early.
I guess on a similar note for the quizzes, can you set them up so like the day after they're due, the scores are automatically?
Is it possible on Gradescope?
I think so.
Okay, let me.
Because I think that would be helpful. It doesn't change the difficulty of the quiz, but if you get something wrong, you remember what you were thinking yesterday.
Okay, let me. But you also like if I suddenly forget, just ping me and let me. I mean, yes, I looked at over them today in the morning and I saw that okay, like a bunch of them are not released. I was under impression actually that the grade is released automatically right away, but it's not apparently.
I think there's some setting.
No, I agree. Okay, let me. If you find the setting, if you're like expert on Gradescope, let me know. Like or like. So okay, release the quizzes early and 06. Release immediately the grades. So again, I argue that you should benefit from the office hours. Like TAs should be reasonably knowledgeable in this class because they were carefully hired. And just come see me. So my regular office hours are Tuesdays 1 to 2. If absolutely necessary, we can do Thursday as well if it will help. And I mean, people are usually coming only when they need help with homework, but you should come and like when you have general questions as well. So what else? Okay, but yeah, go ahead.
Maybe you can provide the version about quiz, like how much chapter you will include in this quiz, so that we can prepare it well.
But like the chapters are assigned online, right? So what information will be helpful, do you think?
I mean, like this quiz deadline is this Friday, and
let me show.
I'm not sure if the lecture today is included in
the quiz
or not.
No, quizzes are only they cover the week before. So everything, so that's why we, like one of your classmates did this pull request and we split the class into those weeks, right? So essentially, if we do a quiz for the previous week, which is already probably February 14, no, this is correct. So this is the previous week, right? So this is what will be covered in a quiz.
This goes back to just talking about the alpha assignment. I think something small that can be helpful on it is just comments in the structs describing like some of the important variables that are relevant to like the parsing and stuff. Like with the type variable and like what the offset is, just like small stuff like that.
So do you think? I mean, I can try to like. I guess I can, but if you already understood, do you think you can create a pull request to do this?
Is that what you mean?
No, if you already understood like what the comments or like, do you think you can provide these comments for me, like or you still don't know the answers?
I think I know at least a quarter of the answers.
Quarter. Okay, quarter. Sure. Let me update. Try to update the homework with the fields. Essentially, the confusing stuff is. Okay, let's try doing this. Let's try to explain what fields are in this. But we really need like 3 fields or like 4 fields, something like that, to create this loop. But I'll try to explain a little better. Yeah.
The Wikipedia page for Elm has like really good, so you just link that. It explains every field and it has almost the exact same names as the structs and the assignment.
Yeah, that's a good idea. So maybe a pull request, or you feel comfortable doing it. Some people are doing it. Yeah. Yeah. So will it be okay with you with the first person? Like I don't know the name. Sorry. So
Yeah, no, I didn't know about that. I'll double check that.
Yeah, no, I'll link. Yeah, that's totally that's a good idea. Okay. Okay, but back to the quizzes. Sorry. Back to the quizzes. Are you fine? Like we always cover the week before in a quiz, even if it's assigned on Wednesday or Tuesday, like today.
Yeah, because each chapter maybe it would define 3 parts. Like last week, we just took the loading and link, but that part just took 2 weeks, two lectures to finish it. Yeah, so the segment is hard to tell what chapter I should start.
A chapter in this linkers and loaders book. Well, technically speaking, I don't even ask you to read the linkers and loaders. It's a huge book, so you just have to read this one. So essentially, the chapter which is linked from here, which is just one chapter, chapter 5, right? So this one. So if you go to chapter 5 here, okay, hold on. It's wrong. Okay, I can scroll, but essentially this is the book, and this is the chapter which you had to read, and this explains actually the ELF. I mean, the person who was asking about the ELF. So this is roughly speaking here, I would say. Let me just quickly go over this book again. So let me just download a copy and go to chapter 5. Still not 5. So essentially this. So like this chapter provides a very detailed explanation of the ELF format, right? So if you, and with all these fields explained, maybe Wikipedia does a better thing, but everything is explained here, right? So but I guess Wikipedia does it a little bit better, right? But that's what you wanted. That's what I wanted you to read. So don't read like everything what is said optional. You don't have to read. Just like you have to rely on the lecture in this case because it's a big book. So like it takes a day to scroll through to understand. But after the lecture, I guess. But again, I don't want you to waste a day on that. Any other suggestions for how to better organize quizzes or homeworks? Yeah.
So could you see that explanation about the correct answer after the quiz is free?
We don't have explanations. The way we, okay, like the best way again is to ask us. So how can we do this? No, I mean, yeah, that's valuable. That's so Piazza doesn't work. So you think that you cannot ask on Piazza and saying, okay, quiz number 4, this and this and this, I made mistake. Why is that? Will it work for you or? Okay, probably the better way of just like to publish the answer. Okay, let me try to work on this as well, but I don't know how to better provide them. Like essentially, what kind of medium to choose. But okay, yeah, let's try it. Let's try providing answers as well. Okay. we'll get back to this hopefully on Thursday as well, just to talk a little bit more about because I see that, you know, like I see that the median on the quiz is slowly dragging down, you know, like, so which means that people are suffering for whatever reason cannot answer. And I agree, and I say material is challenging, so it's okay, but still would be nice to have it a little bit higher. Something else I wanted to ask, so I wanted to say, so typically people, at some point, people get worried about their grades in this class, right? So, and I do realize that the class is challenging, right? So then it's not, I mean, there are multiple ways to teach it. And one way is to say, okay, I'll just like pretend that I will teach you operating systems and you guys will have a warm, fuzzy feeling that you learned something. Well, that's not what we do here. So the way we teach is that if we suddenly end up hiring you as our core, whatever, a team member in my team, which builds operating system, we at least want you to have a chance to, you know, to work this, to at least speak the same language with us and actually be helpful and feel that you can do it. And I believe that you can. And so that's why, I mean, everything is set up in such a manner that everything is very, very real, which makes it challenging, right? Because there are so many details which you have to understand. But on the other hand, to make sure that, you know, we have a somewhat enjoyable learning experience, we never try to be harsh giving you grades. Essentially, like literally just a handful of people out of 200, maybe like 2 or 3 people fail. Maybe like 5 people are below C or something like that. So essentially we curve aggressively, and if it becomes a question, I can dig up historical data to show you what the averages are in this class. So on average, like the amount of people who get A's and A minuses is probably higher than in your regular classes, because we curve everything, you know, so aggressively. So don't worry about the grades, because some people started emailing me, okay, I did this and this, and okay, am I failing the class? It's highly unlikely. So if you submit all the homeworks, do the quizzes, do the exams with any kind of score, then we never fail people who try, essentially. So essentially, like people who maybe like below 30% of the grade fail, which is very hard to achieve. Like getting below 30 means that you stop submitting homeworks or stop submitting quizzes at some point. So again, don't worry about it, despite the fact that it's really challenging. I agree with that, but I mean, there is no real easy way out of it. Okay, any questions about the grades? Usually people, undergrads who come, I mean, grads too, they are very worried, but I guess people who came into the class in person, they are not at this point. Okay, let's get back to this, to paging. So this is somewhat exciting lecture, just because it's, again, it's at the very core of everything, right? And no matter whether you end up doing operating systems or just building something real fast, which involves page tables, sooner or later it will be coming back to your life. So let's understand it. Okay, so we covered last time we talked about segmentation, right? So idea that you can split the memory of the program into regions, and the hardware will essentially control whether you can access the region or not. So remember, the hardware was, let me just scroll back a couple of slides to make sure that we understand them, to understand how segmentation works. So it's a lot of slides back. And back button doesn't always work. Come on. No? Okay, let me switch like this. So remember that the way it was working is this. So the hardware was maintaining a table in memory, which is configured by the operating system. And each process will have its own table called global descriptor table. And operating system will be switching between those tables when it switches between the processes. But the table contained essentially the base and the limit of a segment. And the translation was working like this. So essentially, if you have an address in your register, so for example, here you have an address in the EBX register, and this is the address, then you take the base from the table and add it to this address. So for example, here we are using the yellow global descriptor table. This is the address, this is the base. So we add the address with the base and end up with an address which is provided to the memory controller, right? And hardware as well checks the limits. Essentially, if you try to access memory somewhere over here, so essentially outside of this segment, the hardware will trigger an exception saying, okay, your limit ends here. So you're starting from 0, going to, I don't know, maybe 1 megabyte here, but everything above 1 megabyte will trigger an exception, right? And the operating system will manipulate those tables, essentially providing an illusion of a private address space to each process. So green process has address 0, which is physically at this address, and yellow will have its own address 0, which is translated to this physical address, right? We understand this idea, right? So it's not super hard. So very kind of easy. So the operating system can configure those regions to not overlap. So the green will be here, the yellow will be here, and essentially this guarantees that the green process cannot access memory over yellow process, right? You can imagine scenarios in which you create a special segment which is shared between green and yellow, and that provides you with inter-process communication. So green can write memory into the shared, write memory of that shared segment, and the yellow can read from it, right? Which will allow them to send data from one process to another. Okay, so we talked about it, and then I asked, we arrived to the conclusion that this is not ideal, right? So what was wrong, or what were the limitations of this model? Who can tell me quickly?
Wasn't it hard to like expand if you needed extra memory?
Right, so that was essentially one problem was the segments are too large and don't have enough flexibility. So if you suddenly try to grow the process address space beyond the original guess, you may run into another segment in physical memory, which means that you can move the segment in physical memory transparently, right? But it's expensive just because moving the whole segment, and moving means copying, right? So essentially copying regions of physical memory will take time, right? So what else?
Would it waste memory too? Because if one process doesn't need all the space.
Correct. So you can end up with fragmented memory, meaning that you still have available physical memory, but those pieces are spread all over the place. And like at some point, you have to essentially move everything around to make sure that you can allocate a one continuous region, right? So which is a problem. And plus this paging or like swap in and swap out, essentially taking the processes, the memory of a process which is relatively idle to disk is expensive just because you have to copy the entire segment. You can play tricks and you can say, looks like I can maybe copy only half of it by controlling the limit, but still it's rare that only the beginning of the address space is used versus the end. So there is no such law. So essentially, like usually address space is used uniformly. And another complicated thing is that you cannot really emulate, and maybe I didn't talk about it, but you can't really emulate a larger virtual address space on top of a small physical memory. Because the moment you create a segment, if this is your physical memory and you have maybe like, let's say 16 megabytes, and you say, okay, I want to emulate 64 megabytes of virtual memory, right? Then even if you set a base, if you set a limit, immediately those accesses go nowhere, right? And the memory controller will trigger a machine exception saying, okay, like you're really trying to access an address and I don't have physical memory backing up this address, right? And at some point, maybe less important today, this emulation of large virtual address space on top of a smaller physical memory was a big thing. Why? Because the physical memory was so scarce and so expensive that people were willing to say, like, let me just run a program which really like needs this 64 megabytes of virtual memory, and I will be taking parts of this memory takes part. Not all of it will be present at all the time. Maybe like this region will be present, and this will be present in physical memory, and they will be mapped here and here in physical memory. But those two regions were saved on disk, for example. And only when the process tries to access them, we'll bring them back from disk, like bringing back them here, for example, taking this part first to disk, making sure that, okay, the process can run. Today, it's not an issue because memory became sparse, memory became cheap. Today, there's a different issue. People want to think about local and remote memory. So kind of the same idea, but different. So essentially, in a data center, if you have a server, which, for example, has maybe limited capacity of local memory, let's say 256 megabytes, and there is a very fast network which connects this server to a set of other servers which essentially provide large memories. So maybe in the orders of terabytes. This is the architecture of today. So essentially, this memory is local to you, and you can access it fast. But you do the same emulation. And if the page is not present in this local memory, essentially go here over the network, get the page, and put it here, kind of using this local memory as a cache. So kind of the history repeats itself, but slightly in a different scenario. And this setup in which local and remote memories are used in the data center is motivated by the fact that it allows them to like build this infrastructure in a more flexible manner. You don't have to like, put 512 megabytes of memory in every server, but instead like have some servers with tons of memory and local servers with some limited amount of memory. And you can design those systems in such a way that they are reasonably fast for a reasonably large set of workloads. Some workloads will be penalized like badly, and that's not a good design choice. But some will run okay. Yeah, you had a question.
What is the latency of the network around the speed?
It used to be, but it dropped so significantly that these days this is actually like this is a cutting-edge research. If I ask you to guess this latency, what it will be? Imagine it's the same rack, meaning that you have a same data center rack full of these blades, and you have a top of a rack switch here. So what will be the latency today? Again, eyeball it. It's a useful number.
1 millisecond.
1 millisecond. Let me show you millisecond. Ping google.com. My ping to Google is 16 milliseconds, right? It's my round trip time. Agree with this or disagree? Reasonably fast. It probably goes over a ton of, I don't know, it doesn't matter. So clearly not 16 milliseconds because Google is not here, not in my rack, it's somewhere. So take a better guess. Boy, does anyone know how to trace route is not available anymore? Trace pass? Dig? No, I just wanted to show you the path of a packet. So it goes like, it's a millisecond to probably my gateway in the School of Computing here, right? So 5 milliseconds. I just wanted to, okay, sorry. Just wanted to make sure that, when someone asks you, you can use a tool and figure out what the latency is actually. Like 100 milliseconds is horrible. When I go to Ukraine, I get a latency of 100 milliseconds to my servers here in Utah because it goes over the satellite and stuff like that. So then it's kind of like, okay, you feel the latency. So that's bad. This, we're fine. Another guess. 1 millisecond, so.
A microsecond.
A microsecond. Yeah, it's in the order of microseconds. What's in 1 microsecond? No, like on a 2 gigahertz machine? 2 solid. Right. So modern switches essentially like they are dropping below the 1 microsecond latency. Like 600 nanoseconds one way was possible a couple of years ago. I'm pretty sure that it will become possible soon as well with new interconnect. So if your latency to access a cache line is roughly speaking 250 cycles, if you're dropping in the range of 2000 cycles, you're still 10 times slower, but it's not like horrible. So this is the thing of today. So they're trying to build those servers, try to improve the networking and improve the interconnect in such a way that this idea becomes feasible. It's already deployed in practice, so it will become deployed more aggressively. So anyway, so again, paging, why this detour? Again, you will never maybe, I mean, you might be faced with a problem of optimizing for virtual memory locally, but you most likely will be facing the problem of optimizing your workloads for working in this environment in which some of your memory is local and some is remote, right? Okay, so high-level idea for the paging is to just make it way more flexible. So essentially, split the address space into the chunks of identical size. A typical size is 4 kilobytes on Intel machines, right? Although Intel supports different memory sizes, and we'll come back to it in a second. And then translate, instead of like providing translation for the entire segment. So for example, your entire segment might be this, right? Provide translation for each page individually. So you have some kind of a data structure which says that this page, and imagine we think in terms of page numbers. So this is page number 0, this is page number 1, this is page number 2, and this is page number 3. So you input page number 3, and it tells you the physical address. So this is virtual page number, and this is a physical page number of this page. Maybe this is 55, right? So then you say, okay, if I have this data structure, I will be translating every page individually. Some of those pages might say, wow, it translates to nothing, right? This page is not present. And because it's maybe taken down on disk, just one individual page, right? So for example, I don't know, maybe this one, for example. And this triggers an exception, which is called a page fault. So you probably heard those words, but essentially the operating system says, okay, your page is not present. If I, meaning operating system, took it down to disk temporarily, I will bring it back and they'll let you run forward, because you say like it's totally, you will perceive a performance slowdown, latency of bringing the page back from disk and reconfiguring this data structure which does the translation. But really, everything else will be transparent. We will continue executing from the same instruction, from the same load from memory, for example, so everything will be fine, right? And however, if you say like this page was never allocated to you, that's an exception, right? It's kind of like accessing the segment out of bounds somewhere here, and then you see typically the debug message which you see is a seg fault, but this seg fault is actually materialized as a page fault at the level of the operating system, right? Okay, so if I ask you this question, so how to design this data structure? What will be your idea? Data structure which can translates individual pages or page numbers, virtual page numbers, into physical page numbers. There are multiple options.
Hash table.
A hash table. A hash table is a decent idea. So we will say this is a hash table. We will take a virtual page number, do a hash function on it, right? It will land you on some index, and this will contain your physical page number, right? What are the benefits of hash tables? Why did you choose hash table?
Access time.
What is the access time? 01, yeah, constant. That's good, so it's fast. But for example, why not an array? I can say, why not an array? And I will have an array here. Virtual page number is an index into this array, and this entry contains physical page number. Why would you choose a hash table over an array?
Hash table you can handle like dynamically allocating a little bit easier than an array. You can just add a new or another.
Your array can get extremely large, whereas the hash table is sparse.
Yeah, so what you're saying essentially, the hash table allows you to handle this sparse address space, meaning that you maybe have a page 0, page 55, and page 1 million used, and this will occupy only 3 entries in a hash table, right? So this will be 0, this will be maybe 55, and this will 1,000,007, right? So those are only 3 addresses which you use, and the hash table can contain only 256 entries, right? Agree? Because if you do the array, then you really need to at least as large as this 1 million, right? Agree with this? That's the advantage of a hash tables in general. That's why we use them. Access time and the ability to handle sparse key space, right? So on your key space here is our virtual addresses. Is that clear, right? What are the disadvantages of hash tables?
Well, if we were to resize it, your things, if you want it on static.
Yeah, resizing, major pain. Like there are like there are 2 big directions of how page tables, or 2 big designs of how you build hash tables, and one are essentially, I mean, the difference in how you handle the conflicts. So imagine, I mean, let's talk about conflicts first for a second, because it's another problem, conflicts. So in one way, you say, look, I will land on this entry, and maybe I will contain a linked list of all the entries which, because maybe you have only 256 entries to begin with in this array, right? And you say entries 55 and 77, they hash into the same bin, right? And then you keep allocating this linked list, right? And that's how hash tables are one way to build them, right? And so the disadvantage of this approach is that first you need to dynamically allocate those elements, right? Which is kind of expensive. And second, every time you want to walk this list, you have to essentially access memory to read the next element, right? And the second school is essentially say, look, if I hash on this bin, I will do something what is called linear or quadratic probing. I will try to essentially try the bin after it, and if it's available, that's my bin which I will be using, right? And that's a little bit faster because you usually have spatial locality. You just access the same cache lines, but again, resizing kind of kills the deal, right? In this case, because at some point you say, look, my hash table is almost full. Sometimes you say, look, and this approach loses performance dramatically as you approach as you saturate this hash table above 75% essentially. Then you say, look, I almost have to walk the entire thing in a circle to find an empty bin, right? And deletion is hard because you can't really delete. You need to mark it as dead, but you can't really reuse the space until you resize, right? And so imagine building this algorithm in hardware. It's a little funky. It's possible, it's doable, but a little non-trivial. So amount of gates which you put in it, and the operating system will say, look, imagine running it and say I have to resize. Where do you even get the memory from? You need a memory allocator. Normally it's just malloc, but here, hardware doesn't have malloc. You can build it obviously, but it's not a good idea. Okay. Is my argument clear that hash tables are probably not the best idea? Arrays, which I will be suggesting as possible approach, seem to work, but as you indicated correctly, they just immediately grow large. Let's just eyeball the size of this array, just to understand how large it gets. So in this specific example, I'd say, okay, let's use an array. So essentially, we take the virtual page number from the address, right? So by the way, so if we split the address space in the chunks of 4 kilobyte, right? How many of those pages we have to handle? The total address space is 4 gigabytes. So how many? 5,000. 4 billions divided by 4,000. What is it? 4 millions, right? No, not 4, just 1. There's 4. So really, yeah, you have to handle translation for 1 million pages. So this is the exact number if you speak in terms of powers of 2, right? So your array has to have 1 million elements, right? Agree with that? 1 million elements. So if I ask you the question, how big is this array? Can you eyeball the size? Let me go to this big figure here. And back doesn't always work for me. Previous. No, yeah. How big is the array? 1 million entries. How big is one entry? What do you think? For you to do a translation. 4 bytes. Why 4 bytes? No, because you're okay. If you really need to represent 1 million, your input is you say my input is 1 million possible combination of virtual page numbers. My output is 1 million of possible physical page numbers, right? So it's not really 4 bytes because 4 bytes is 4 billions and you only need to handle million, right? So to represent 1 million numbers, how many bits do you guys need? I'll give you a hint. It's 20 bits, right? So 20 bits is a little bit less than 4 bytes. I just wanted to make sure that we understand those numbers, right? Because literally, if you say this is 1 million entries, you really need only 20 bits to represent 1 million entries. Or like I'm rounding, but like this is the exact number in powers of 2, right? However, you also need to store access flags. Maybe the page is read-only. Maybe the page is writable, right? Maybe the page is accessible by the kernel and maybe not on the user level, right? So which brings us back to 4 bytes because the 20 bits for the translation and the other 12 bits for the flags, right? Just round up to 4 bytes. So then your translation array is really 4 megabytes, right? That's kind of sucks, right? Because remember, on my early machines, I mean, my physical memory was maybe 16 megabytes total. And if you say I need an array, then it really takes like 4 megabytes, like 1/4 of this address space, right? But in theory, this is possible. The hardware could have a register, let's call it control register 3, and this is how it's called on Intel, which says, okay, your beginning of this array is in the page number 2, and then this is the translation array, right? And you say, I will take the 20 bits of your address because the lowest 12 bits, right? 12 bits, by the way, represent 4 kilobytes. It's just an offset within the page, right? So it's no matter which combination you choose, you start from byte number 0 within the page, go to the last byte, which is 4095, last byte of a page, right? But these 20 bits represent one of possible 1 million virtual page numbers, right? And then we use it as an index, like in this specific example, if it translates those bits into decimal numbers, your number will be 1040, right? And this is an index in the array, and the entry is there 12. So you say that this page is really physical page number 12, right? So this is possible to do, but the insanity of it is the size of this array. You have to deal it. So hash table is too hard to build because of resizing and the complicated logic. And despite the fact that the access is 01, the constants hidden in this 01 can be large, right? So it can be like 3-4 times larger than accessing doing one memory access to access this array, right? Okay, I'll ask you again. So can we do a little bit better? We say, okay, look, maybe I don't need the whole array. let's just say I'll have array with a size, right? It's natural idea. You say, I know that like my cat program is tiny. Maybe it has like 3 pages total, right? So one for the text, one for the data. Okay, one for the stack and one for the heap. So 4 pages total, right? Why not? And you say like my array really will contain a size somewhere, and it's only like has to translate 4 pages. So most likely it will fit in 1 or 2 pages here, right? Right, because then you only need like a handful of entries. Is that a good idea? Array with a size.
If I remember from a previous class, we have the upper memory allocated to the operating system and the lower memory allocated to the app. So we've got this big gap to get to those upper address pages.
That's correct too. As operating system designers, we can address your problem and move the operating system in front. Then you know it always will be there. And then still put the address space of the program after that. But what real problem is that it still does not allow you to handle a sparse address space, a case in which you say, I allocated like at some peak point when I was loading my program or something, like a ton of pages, my size grew to this large number, but then I don't really use those gaps, right? So my address space is sparse again, right? So because again, you still need to support the case when you reach the very end of this address space, right? And this relates to what you were saying, right? Agree that this is still a problem. So it's not gonna fly. Why I'm covering this? Because in your real life, there will be a case when you will have to design a similar translation data structure. It will not be page table. Maybe it will be virtual blocks on your block device translating to a physical block sectors, which you will send to disk or something, right? So maybe it will be some layout in a file. And those options kind of naturally come to mind. And then, you know, you will have through the same design process, and hopefully you will, you know, filter out arrays with sizes, right? If I ask you this question, so look at this picture and think about the data structure, which will allow you to represent naturally the case when your address space might be sparse and only parts of it are used. So how would you do this?
Maybe a tree.
Maybe a tree, exactly. So why a tree? How does tree help?
It only represents data that's there.
It only represents what?
Data that is there.
That is there. So how will you construct such tree, which only represents the data which is there? What is this tree? I mean, you're on the right track. The page table is a tree. Now, just let's understand why this tree is chosen to be this way, the way it is designed. There's a very natural observation here. It kind of comes from combining these two ideas, arrays with sizes and sparsity. You say, let's split this address space in chunks of equal size. Let's say, I don't know, some number, let's say 4 megabytes, right? And you say, I will have a translation array for each chunk. It's reasonably small because it's 4 megabytes. It only has to contain 1,000 entries, right? 1,024 to be precise, right? Agree? So you say, look, I will say there will be an array of 1,024 entries, which will be translating pages in this region, right? If I don't use the next region of 4 megabytes, I will not allocate an array. I don't have it. I don't need it, right? I will say, what about this region? I'm using it, so that's okay. We'll say there will be a translation array for this region. Again, 1,024 entries, because every region is fixed size, right? For this one, don't have it. And for this one, well, we do have it. And maybe not all entries here are useful, right? Because some of them may be translating something what I'm not using, right? So, but still, nevertheless, if I essentially use a region, I waste 1,024 elements, which is multiplied by 4 bytes, so which is 4 kilobytes, right? Agree? Okay, seems natural, right? So just have an array for a region. Now the question is like, how do I get from addresses to those arrays? But this is where the tree comes from, because you say, look, I split my address space into regions. This is region number, let's say 0. This is region number 1. This is region number 2, number 3, number 4. I will add another layer of this for this tree. And I will say for region number 0, I will have a pointer here connecting, saying, okay, for region number 0, this is your translation array. Agree? For region number 1, I'm not using it, so this is empty. Now, for region number 2, I'm using it. So this is a pointer to this second level, right? For now, region number 3, again, null because we're not using it. And for region number 5 or number 4, we have a pointer, right? And again, since like it seems kind of natural, you say, look, okay, my total address space is 4 gigabytes, right? So which means that if I split it into regions of 4 megabytes, I will end up with 1024 possible regions. Agree? If you design a data structure like this, this allows you to combine the best of these two worlds. You say, look, if I handle the sparse address space, I only wasted 4 kilobytes for the root, right? 4 kilobytes for this, and for this, a total of like 16 kilobytes, right? So it's like not 4 megabytes for the array, just 16 kilobytes. The translation is much easier than a hash table because there are no conflicts. You don't have to resize. If you say, I'm going to start using this region suddenly, then you fix this pointer. You just figure out the space for this. There is a little bit of a location, but you figure out the space for this array, and then you start like essentially adding entries here, right? Any questions?
So isn't this kind of like a hash table of hash tables where the hash function is just certain bits of the memory?
I would say it's in a way, it's an array of arrays, right? The hash table, the major property of a hash table that it compresses the key space. You say, I have 1 million keys, and I will use a hash function which permutes nicely and compresses the key space into maybe 1024 entries. There is no compression here. We just say, look, it's either present or not. But you can play tricks with hash tables of hash tables, but this is just simpler, I guess. And this is essentially how the page table is built on x86 hardware and on any other hardware as well, almost any other hardware.
This is, we're looking at a 32-bit address space.
Correct.
So a 64-bit address space would do the same thing, but add more layers to the tree?
Correct. So specifically, you say, my tree right now represents 4 gigabytes. If you have more, well, let's split the chunks of 4 gigabytes here and add another layer here, right? Which will allow me to represent the address space of 4 gigabytes multiplied by 1024, for example, right? If you add 3 layers. And this is what effectively 64-bit machines are doing. They used to have 4 layers, and now they added the 5th one because they ran out of space for layers. But again, we got the idea. So tree is nice, and more specifically, it's called the radix tree, right? Radix means that radix can be like 2, essentially. Each node comes into 2 subnodes, right? Or in this case, it's a radix of 1024, right? But it's natural here because you say like, do I have an array below me? Yes. Then go and look it up. And let me ask you a question. So what do we keep in this entry? Let me just change the color so I can highlight for everyone blue. So what is inside this entry? A pointer. What is a pointer in this case? An address. More specifically, it will be a physical page number of the page which contains your translation array, right? And if I ask you, what do we keep here in this cell? Like this one, like for people who were writing. What is there? Yeah, again, you can say a pointer, but again, I will say that it's a physical page number of an actual page where the virtual page is located, right? Okay, let me just go through the example. So this is exactly the same idea, right? So just to make sure that how it works for the addresses, right? If this is your 32-bit address, remember we split the address space into regions. So region number 1, which is, I will take, since I took 1024 regions, that will be 10 bits, right? So region number 1 will land us in the entry number 1 of this array, right? And in that subregion, we will again use this 10 bits here to essentially like pick an entry in this array. Let me just again like emphasize a little bit. Like I'll go through the examples in more detail. So by the way I split the address space, it naturally fits, the arrays themselves naturally fit in pages, right? Because I chose the sizes wisely. So I said my page size, one page is 4 kilobytes or 4096 bytes, right? I say that my array is 1024 entries. Each of them are 4 bytes, which is 4096 bytes, right? So, which means that this thing can be actually stored in one of those pages, and it fits exactly in the page, right? My second level of like translation is the same idea. So 1024 entries by 4 bytes equals 4094 bytes, and it fits into the page, right? So that's kind of like alignment works nicely for us. So those elements of the tree are saved in individual pages. And so, for example, here, the hardware says, okay, the root of the page table sits in the page number 2. This is the page number 2, physical page number 2. And this array physically sits in this page. When you're translating this address, you say, since there is 1 here, I will pick the entry number 1 in this first level. It contains physical page number 8 plus some additional flags. So you go to physical page number 8. It's like not you, but the hardware does it. The hardware goes here, reads the entry, and you say, look, this is my translation array. And then you say, what is this entry? You translate this to a number. You pick a number here, and this will contain the actual physical page. Let me just illustrate one more time, but with a concrete example, right? So this is a full translation. By the way, segmentation is always on. Like just for a second, let's imagine that the base of the segment is 0. So the hardware adds the base, but it doesn't change your address. So AT&T assembly syntax here. So EBX contains an address, right? So EBX is this value in decimal. And if you represent it in a hex, this is the 32-bit address. Oh, no, sorry, not hex, in binary, right? Okay, cool. So we have, as I was saying, 1 million entries in our address space. So this is the virtual memory. And the physical memory is very, very tiny, only 12 pages. Imagine I'm like so cheap, I just bought a microcontroller which has only 12 pages, right? Okay, so we call this a page number, the top 20 bits, right? Because the top 20 bits define the page, right? And the lowest 12 bits are an offset within the page, right? So the page number in this specific example is 5123. So it's essentially, if you take those bits 101, 00, 00, 000, 0011, right? This is the number, and this is in the same number in decimal, right? So what do we do with this number, 5123? We know that this is the virtual page numbers, but this is not how the translation works, right? So what we have to do is the first, we have to locate where is this first level of the tree located in physical memory, right? So first level of a tree in physical memory is maintained by the hardware. So operating system says, okay, I will, when I start a process, I will update this register, which is called control register number 3. Just on Intel, it doesn't matter. Like it might be called something else on ARM, like page table directory register, for example, right? So you say, look, in a page number 0, there will be a root of my page table, right? So this is my first level of this data structure, which is called page table directory, right? Or page table, and this first level has a canonical name, page table directory, right? Okay, so now we say which entry out of all of these entries we have to choose. So which one? Do you know? Say again? 5, exactly. So because we take this top 10 bits and look at them, and this number 101 is 5. So where is it? Number 5, right? Right? Okay, so as I was saying, in order to locate the next level, we need a page number, physical page number. This is physical memory. Physical page number takes only 20 bits, right, to represent, because it's, again, just 1 million pages. But the rest are flags. So this address, this number will be contained here. Okay, the hardware will read this number. Imagine it's 7. For whatever reason, the operating system just configured it to be 7. So the next level of translation is in the tree. Again, which entry we pick here in this second level? Which one? 3. Okay, yeah, we know how to translate. We translate this 311 binary into an entry. Where is it? Okay, entry number 3, and this will contain the actual physical page number of a page where this address is located. So let's say 12, right? So this is the actual, this 12 is the actual physical page which contains the data. And this lowest 12 bits is an offset within the page, right? So right now it's byte number 1. So this is the byte number 1, and it's here. Let's say it contains 55, right? So since it was a move instruction, which was the loop, okay, the way I wrote it, it doesn't say a byte, but let's imagine it reads a byte, just for the simplicity of the argument. So then register EBX will get this, EAX, sorry, because you're moving from here to here, EAX will get the number 55, right? So this is what the hardware will do underneath. So is this clear? The page tables, like, idea is intuitive. Split the address space, tree, just walk the tree. At the end, you will find the translation address. Any questions?
Wouldn't this be overkill for this has memory? Because we used to use like a lot of space for this whole process.
In this specific artificial example in which I say only 12, yeah, I agree. It will be an overkill because you lost 3 pages just to translate. You lost, like, you know, what is it? 1/4 of your available physical memory roughly. But it's just for the sake of example. So this really never happens in practice. So typically, the smallest physical memories were in the order of 4 megabytes. And then they probably maybe 1 to 4 megabytes on first machines, which deployed this paging idea, which is Intel 3386 architecture, like this, right? So, and then the memory started growing, and today we have terabytes of memory essentially available, right? Any other questions? Okay, let me just go ahead with yet another example, or just reiteration of the same idea, because people tend to get confused about it. So again, if you open an Intel manual, the 32-bit version, you will see this picture there. Mine is from a couple of years ago. The updated one will have blue colors. But the idea is the same. So remember, segmentation translates from logical address to linear address. So after segmentation is done, imagine you have a linear address. The translation goes like this. You take the hardware takes the control register 3, takes the 32 bits, and says, okay, look, this is where the root of the page table is in physical memory. Then you split this into, you split the linear address into like a triple of 10, 10, and 12 bits, right? The first 10, the highest 10 bits define your region. And so essentially it's an entry. So I show it like this. So this 10 bits, which chooses an entry in a page table directory, right? The output of it is this 20 bits, right, which to locate this, the second level of translation, right? And if you look at this entry, it's called page table directory entry. It will contain the address of the page table, like 20 bits of address, that's what we need. And the rest are the flags, right? So there will be something like a flag. This bit 0 will tell you whether this entry is valid or not. If you have a 0 here, it's immediately a page fault because this entry is not valid. So you have to set it to 1. This controls readable or writable. This controls accessible by the user code or only by the super user or the kernel. This bit controls whether the page was accessed, so allows you to essentially track whether the page was accessed, to maintain the statistics about how often the page is accessed, and essentially whether it's a good candidate to swap out either on disk or, as I said, in modern world, to put it into remote memory on another machine, right? And some other bits I probably less relevant right now. There was a set of bits which were ignored, but can potentially be used today on modern machines to implement various security schemes, right? But back then they were not used. Okay, oops, sorry. So we understand why it's a 20-bit address. By the way, why? Why is it 20 bits versus 32 bits? Do you understand? Just wanted to emphasize.
The pages are 4K, then that means that the remaining bits are the address within the page.
Remember how it goes. This CR3 points, it actually uses 32. And then this one points to, again, it's a page in physical memory. This is physical. And I agree with the fact that this is a page, 4 kilobytes, right? But you know, 4 kilobytes, it's still, physical can be from 0 to 4 gigabytes, which would say a lot, says, okay, it requires 32 bits if this page can be anywhere. So how come we go down to 20?
It's because we don't use the address of the page, we use the page number.
And what does it imply in real terms? I agree with this, but the assumption, implicit assumption, or explicit assumption, if you like, is that those pages are always aligned at the page boundary. What does it mean? So no matter if it's always aligned, then the lowest, no matter which page you take, the lowest 12 bits of the address will always be zeros, right? It doesn't make sense to store zeros around. You already know that those are zeros if everything is aligned. That's why it frees up the space for these bits, because otherwise you would be just storing zeros. And that's a trade-off. If you say, I don't want alignment, I want to put page anywhere, then you lose, and you have to use those bits to keep this all like byte accurate address of a page. But if you say that, okay, I require that all pages or all pages are always aligned to a page boundary, then that's your win, essentially. That's a design decision which you make to make sure that you can save the space, right? Agree? So alignment, that's what I wanted to hear, essentially. So this essentially, alignment allows you to talk in terms of physical and virtual page numbers. Okay, so then you go to this second level of translation. You use this 10 bits, sorry. This is 10. Again, choose an entry in this array, and this contains a page table entry, which is very similar. Again, 20 bits of address, flags. Again, this bit number 0 says whether the entry is valid or not, whether the page is readable or writable, whether it's accessible by the user or super user code, whether the page was accessed, and whether the page is dirty, meaning that not only you track accesses, but you can track writes into the page, which then later allows you to implement schemes like virtual machine migration. You say, look, I copied the memory of the entire machine, virtual machine, but it was running, so it was updating more pages as I was copying. And then you walk the page table and say, you pause the machine for a second, maybe it's running Quake. You pause it for a second, you only copy the pages which were dirty, which were accessed and written in this period of time. And it's a small subset, maybe it's like 1,000 pages. So it takes you like tens of milliseconds. And then the human which plays Quake barely perceives it, but because you lose this round, of course. Okay, but you got the point. So, so some important flags here, right? But similar entry. And then finally, those 12 bits are an actual offset within the page, right? So byte number 0 is here, byte number 4095 is right here, right? So and this is all possible combinations. If you have all ones here, you land on this last byte, right? Agree? Again, reasonably easy, but again, gets a little bit frustrating in practice. And so what did we gain out of it? So again, we first can represent the sparse address space much more efficiently, right? So if we are using an array, we would have to allocate it upfront. but in a sparse header space, we only allocate the root of the page table and then additional leaves in the second level as we go, essentially, as we need them, right? And so the minimal page table size, okay, if I ask you a question, what is the minimal page table size? What do you think? It's a Google style / Microsoft or whatever, Facebook interview style question. So what is the minimal size of a page table which you can create? We'll come back to it later. A little hard, but okay. What's your guess?
It depends on how big the pages are, how big the memory is, how big the address space you have.
In our x86 32-bit system, pages are 4 kilobytes. Imagine you're running the tiniest program, which uses maybe 1 page of virtual addresses. What will be the smallest page table? Like, what's the guess? 2, 3?
You need 2 pages for your page table, and then 1 page for the actual program itself.
Yeah, good. But you may not make it to Google, if you want to go to Google, of course. The real question here, design challenge is, can you bring it down to 1? Can you make loops like this? You can. It's a little hard, but okay, think about it and we will come back later. No one does it in practice, but if someone asks you, you should understand how it can be done. Okay, let me stop here. We will quickly finish the address translation. We're almost there, just a couple of bits, and then we'll start booting operating systems on Thursday. Thank you.